Students, today I'll show you how to find out the value of selectivity for two different cases in liquid-liquid extraction or solvent extraction process. It's well known that the value of selectivity is one of the most important factor while determining or selecting a particular solvent for liquid-liquid extraction system. And the value of selectivity or the solubility of a solvent for the solute should be maximum. So it basically suggests that the miscibility or the solubility of the solvent for the solute should be the highest, and the miscibility or solubility of the solvent for the carrier is or should be minimum or as low as possible. Having explained so, if you want to write a mathematical expression for selectivity, it can be shown like this. Selectivity is represented by beta of solute C over carrier A by a solvent B is the ratio of ratios, where in the numerator you have the YC over YA term. It basically means the weight fraction or the mass fraction of solute in the extract phase to that of carrier in the extract phase divided by mass fraction or weight fraction of solute in the raffinate phase to that of mass fraction or weight fraction of carrier in the raffinate phase. Y stands for extract phase and X stands for raffinate phase. That is how selectivity is mathematically represented, and the value of selectivity beta should be far greater than 1. Okay, if the value of beta is equal to 1, then separation via solvent extraction is not possible, and if the value of beta is closely equal to 1, I mean like close to 1, it means like suppose 1.1, in that range, okay, close to 1, physically it means that if you want to carry out a separation by solvent extraction, one would require maximum number of stages, or the whole plant requirement would be much bigger or higher, and practically it will be untenable. Okay, so a solvent should be picked in such a way so that the value of selectivity is far away or far bigger than 1. Okay, now in the beginning I told you I'll show you how to find out the value of selectivity for two different cases. Now suppose we first discuss case A. In that case, suppose we want to find out the value of selectivity at the plate point. At plate point, okay, what would be the value of beta? Okay, to explain that or to show that, let me first draw a right angle triangle and represent the LLE data within this. The x-axis is the solvent side, the y-axis is the solute side, and then suppose we have a typical type 1 ternary system. So you have a type 1 type LLE, and within that your tie lines may be diverging away from the base with a positive slope, or it may be converging towards the base with a negative slope. Okay, in this way you keep on moving. Finally we come across a situation where the tie line basically reduces into a point, which is the plate point. Okay, now at this plate point, what will be the value of selectivity? Fine. Now you understand that at plate point, if you want to find out the value of XC or YC, it's going to be the same. Similarly, if you want to find out the value of XB or YB, it's going to be the same. So at plate point, XC is going to be equal to YC and XB is going to be equal to YB. in a right angled triangular diagram. However, to find out the selectivity, we are supposed to find out the value of XA and YA. It can be easily found out because we know that in any given phase, whether it's extract or raffinate, okay, in any given phase, whether it is extract or raffinate, XA plus YA, XA plus XB plus XC is going to be equal to 1. Similarly, YA plus YB plus YC is going to be equal to 1. So, the value of XA also is going to be equal to YA. Okay. So, at plate point, your carrier concentration in the raffinate to that of in extract is going to be the same. Similarly, solvent concentrations are going to be same and solute concentrations are going to be same. However, it does not mean that XA is going to be equal to XB is going to be equal to XC, or YA is going to be equal to YB is going to be equal to YC. So this is not happening. This is not the case. This is the case happening at the plate point. Defined so, you can easily find out the value of selectivity at plate point. So at plate point, since you can write it in this way, YC over XC multiplied by XA over YA. Since at plate point XC equal to YC, the value is equal to 1, so it is 1 XC divided by YA, XA equal to YA at plate point. So all are 1, so the answer is 1. So the value of selectivity at the plate point is 1. So at plate point, basically you can no longer carry out separation via solvent extraction method. Okay. Now comes the second scenario. And what is the second scenario? Second scenario is, suppose an ideal scenario where solvent B and carrier A. So this is solvent, this is carrier. They have complete immiscibility into each other. They are having complete immiscibility into each other. Okay. If such a scenario arises, it basically means that when the two phases separates out, suppose this is the extract phase, this is the raffinate phase, and the solvent B and the carrier A are completely immiscible. Okay. So it basically means that when the two phases separates out, in the extract phase you are going to get solute, and it is the solvent rich phase, so solvents will be present and no carrier. Here no carrier will be present in the extract. Okay. Likewise, in the raffinate, which is a carrier rich phase, you will have some solute plus carrier but no solvent present. Okay, no solvent present. So technically speaking, YA is going to be 0 and XB is going to be 0 over here. Okay. Now I already explained the mathematical formula for selectivity. So this is the case. So when complete immiscibility happens between the solvent and the carrier, you will have some value of solute in the extract, some value of solute in the extract, some value of solute in the raffinate. However, the value of YA in the extract is going to be equal to 0 because it's completely immiscible. No carrier is going into the extract phase, so the value of Ya is going to be equal to 0. If that is 0, so it basically means YCXA divided by XC whole divided by 0. It basically means infinity, undefined. Okay, so the value of selectivity is going to be equal to infinity when there is complete immiscibility between the solvent and the carrier, and it's absolutely an ideal scenario. And if such a value, if such a situation arises, that would be very good from industrial point of view, but we rarely come across a situation where the solvent and the carrier are completely immiscible into each other. But that is the case when you can pick a solvent which will be completely miscible with the carrier, giving you a very high value of selectivity, meaning a very high separation. Thank you very much.